All right, hello everyone. I've got a request from someone regarding how do you solve question 14 in the homework. So I'm going to go over that. What's the exact process? What are the concepts? What are you thinking of, or what's going on, you know, as you're trying to solve this? Okay, so we've got, there we go, 125 milliliter sample that is 0.0117 molar nickel chloride. And it's mixed with a 175 milliliters of a 0.250 molar ammonia solution. And we want to know what's the concentration of that nickel 2 plus ion after we mix these and after these solutions reach equilibrium. So usually nickel chloride, it's a salt. We've got the nickel metal, chloride, non-metal. That'd be a solid, and it would dissolve when we or it would dissociate when we dissolve it in water, and it's going to give us that nickel 2 plus and two of these Cl minus aqueous ions. Now, nickel will also form a complex with the ligand ammonia. So we've got, in that case, Ni2 plus 6NH3. If you're not sure what complex it forms or how many ammonias mix with this, you could look this up. Book on page, it's in chapter 18 at the very end. You have section 18.8, tells you all those different complex ion equilibria. You can find this one on page 845. So page 845 shows you those complexes and their formation constants. And then we make that compound right there. So we're going to use that formation to figure out how much of that nickel essentially we're going to pull out of solution and complex with the ammonia, and what's the final concentration then of that nickel ion all by itself at the end of this. So we'll clear this, and let's see, we're going to start with finding the initial concentration of nickel from our first solution. We're going to take that 125 milliliters or 0.125 liters. We're going to multiply that by the original concentration or the molarity. And that's going to give us 1.4625 times 10 to the negative 3 moles of nickel. For every nickel chloride, we have just one nickel ion. So however many moles of the whole thing we'd have the same number of moles of nickel. So we've got, oh, yep, that many moles. And then we need to find out how many or what the concentration is in molarity. So we're going to take that number of moles and we mixed two solutions together. So we need to take the new volume, that'd be the 125 milliliters plus 175 milliliters, gives us 300 milliliters or 0.3 liters. And when we divide by that, we get 4.875 times 10 to the negative 3 molarity. So we have the concentration now for our nickel ion. And we can do the same thing for our ammonia. In that case, it'd be 0.175 liters times its concentration, which was 0.25 moles per liter. Gets us to this many moles. And then we would divide that again by our new volume to get the concentration in molarity. Point 0.1458 molarity for the ammonia. All right, so we have the concentration now of both the nickel ion and the ammonia. So we can set up our reaction and our ice table. All right, so here's the reaction with the nickel ion in the solution, how it's going to react with the ammonia and complex and form that final complex there. And we have a K sub F for this, which I believe is 2 times 10 to the 8th. Yep. Okay. So we found our starting concentrations of these, so we can put those 4.875 times 10 to the negative 3 and 0.1458 and 0. All right, so this is the big concept, or this is probably the hardest part, is how you're going to think of this now. We have our formation constant, our K sub F, and that's pretty large. That's, what is that, 200 million? Yeah, 200 million, pretty big. So what we can say then is this complex is really likely to form. This is very much favored towards the product side. So based on that, we're essentially going to say, you know what? We have only a small amount of nickel here, and since this is very likely to form, we're not really going to use up all of it, but we're going to use up very close to all of it. So in terms of looking at what is our change going to be, we could say it's going to be negative 4.875 times 10 to the negative 3. For ammonia, we have 6 of those that are going to react with that. So we would take our 4.875 times 10 to the negative 3. We'd multiply that by 6. That should give us a change of, yep, 0.02925. And then we're going to form the same number of these. For every nickel that reacts, we form 1 of that complex. So that would be a plus 4.875 times 10 to the negative 3. And then what we're actually going to solve for, so we'll have this as our ending concentration of this. If we subtract 0.02925 from 0.1458, we get 0.11655. Now, we're going to end up very close to 0 amount of nickel, but we're not actually going to have 0 nickel. We'll have a little tiny bit left. And that's actually what the question is asking us for. So in terms of how much of that nickel ion we're going to have at the end for that, we're going to put X. And then we're just putting it into our equation. So our K sub F, 2 times 10 to the 8th, is going to equal our product, that nickel ammonia complex, or nickel hexaammonia. And we have a value for that, 4.875 times 10 to the negative 3. That's going to be over our reactant. The nickel 2 plus ion, that's X. And we have a concentration for our ammonia. And since the ammonia has a coefficient of 6 in front of it, we would take that to the sixth power. So that should give us, let's see, yeah, x will then be equal to, and that should give us, yep, x is going to be equal to 9.73 times 10 to the -6. Or in other words, that's our concentration or the molarity of the nickel 2 plus ion in our solution. So with these, a little different than the other ice tables we've worked with, because our Ks are usually very large and not small. What that means is we can typically assume that the vast majority of that sample is going to react away. And that will allow us then to figure out exactly how much does that concentration go down, exactly how much does that go up, and then, what values can we put in our final K equation there. So hopefully this helps with that. You have similar problems to this. You have at least one worked example like this, I know, in your textbook. So maybe look over that and then try a couple of those end of chapter problems. And I will see you tomorrow.